Okay, we'll start today with some try this. Okay, we won't take time on the video, but if you want to stop and then try that, please do. So if we look at the first one, we're going to get a Diels-Alder, right? So let's look at the mechanism. So this is going to make a pi bond there. It's going to go there. Until you start getting good at these, feel free to draw in a little dotted line there. That's just to help you, it's just guidelines. So we're going to make a 6-membered ring, right? And then remember that if the dienophile, that's the one with just one double bond there, if it's cis, then, right? So this was cis, so then our product is cis. Remember, Diels-Alder has several different ways of doing these reactions. Okay, so if we look at this next one, right here again, we're going to get these reactions to occur, but we've got two different products, and so if we want to look at the major product, right, we could get this product, where we are, just like I have it set up there, right, double bond, or we end up with the carbonyl here. Let me clean that up. Like this, right? And what we know is that if we draw the resonance structures, that will end up with, right, a partial negative there, and we would have ended up with a partial positive here. And so therefore, this is the major product, right? So that 1,4 arrangement. Okay. The other thing we talked about on Diels-Alder on the last lecture was endo and exo, right? So make sure that you review that, and there'll be some practice problems online for that. Okay. Today, what we're going to look at is some other paracyclic reactions. And what we'll start with is kind of a review of the Diels-Alder. And remember, we talked a little bit about the HOMO and LUMO. So if we looked at our structures here, right, so we've got our things. Remember, we talked about, I joked about string theory. So here we got our dienophile. Let's do a little shading. So on the bottom one, right, they are all communicating. And then we get one node. And then we get two nodes. We get three nodes, right? And here is going to be our energy on the other side, right? We're going to get both of these here. And then we can see we've got there, right? So what we talked about is we're going to react our HOMO highest occupied molecular orbital with our LUMO. And so we're going to have those two reacting together. And the nice thing about the Diels-Alder reaction is that when we look at those, right, we've got our shading here. So that the LUMO and the HOMO are in the right orientation, if we think about our in phase and out of phase, to react, okay? And what we'll be doing, right, is taking the electrons from our HOMO and moving those into our LUMO, okay? So that works out very nicely to give us, okay, term known as conservation of orbital symmetry for that process. Now, if we wanted to do the same thing, so this is known as symmetrically allowed. Or symmetry allowed. This is a symmetry allowed process. Okay. Now, if we think about then, let's take some other potential dienes. Let's say that we wanted to take these two molecules, right, two ethylenes, and we wanted to end up with this cyclohexane, so a 2+2. We know the Diels-Alder can also be referred to as a 2+ or a 4+2. But in the 2+2, let's look. If this is just the HOMO reacting with the HOMO, what happens is, if we look again at our species, so let's put, here's the molecular orbital for one, here's the molecular orbital for the other. We put in our shading, right? That's going to be shaded, and it's going to be shaded. Then over here, shaded. Then whenever we're reacting our LUMO with our HOMO, right? Now we have a problem, right? So when we look at these, this, I'll clean that up. So if we look at this HOMO, right, with this LUMO, okay, we see that that lines up, right, but this doesn't. So this is symmetrically disallowed, right? It's forbidden. So we can't do that this way. So what we need to do is we need to alter one of these states, right? So what we're going to do is we're going to hit this with light. So remember, if we take this species, let's put in our electrons, do our shading. What happens is we're going to excite one of those, so we get to the excited state. And that's going to change our geometry. So now in the excited state, now we can look at those two interacting. So if we look at the HOMO of the excited state, with the LUMO of the ground state. Now we can get that reaction to occur. So for this reaction, right, we can do this reaction, but we have to add light. So 2 + 2 needs to go to the excited state to get to the reaction. Okay. Let's look at electrocyclic reactions real quick. If you remember from the last lecture, electrocyclic reactions, we're going to be moving electrons again in a circle, but this time instead of bringing 2 molecules together, we're doing it all in the same, so we don't have a diene-dienophile. But what ends up happening is we turn one of the pi bonds into a sigma bond. Okay. If we look at the reaction, now we can drive these forward by heat. Let me give myself a little bit more room. If we use light, it turns out that what we can do is change the structures of these going back and forth. And this has to do with our HOMOs and LUMOs and the excited state, right? So we can go back and forth between these by choosing whether we use light or heat, right? So if we take this first one where we have the 2 CH3s pointing outward, right? And we use heat, we get the cis form, but then we use light, we can change it to this form where we have 1 pointing in, 1 pointing out. Again, heat, right? We're going to get a certain rotation with heat, and then we're going to get our product. The reason for this has to do with the outside HOMO and LUMO gaps, right? So if we think about our if we think about our HOMO species and what's going to be happening as far as right, for this to react here, these are going to have to rotate in, right? And since they're rotating in, right, that's how we end up with both of these up. But if we're using light, so this is the ground state, but if we use light, that means we're getting to the excited state. So in the excited state, we're not dealing with that. We're dealing with the one that had, so we have this, more nodes, right? Not 3 nodes. So 3 nodes, 1, 2, 3, got 3 nodes. So on this one, right, one of these has to turn. So instead of them both turning the same direction, this one's turning this way, but then that one's got to be turning the other way, right? And so that's why we end up with this change, right? Is that you can think about it as dis and con rotatory. So you're moving them towards each other, or you're moving them out from each other. Now, both of these work. It really depends on whether it's an excited state, and since you can't read that, this is light, right? And this is heat. So this is disrotatory. Right, and then when you're using light, then you're going to be going disrotatory, conrotatory. The way we would see this, right, is that we have something in that conformation, right, and we hit this with heat. In this case, right, we're going to get disrotatory. Right? So if we start with them both out like this, right, then we're going to get disrotatory. That's going to give us both going up, okay, to give us this cis product. Okay. So sigmatropic rearrangements. Okay, our next one. Okay. This one, remember what we're doing here is we are starting with 2 pi bonds. We're going to hit that with heat, and we're going to end up with the same pi bonds, just a rearrangement. So again, this is electrons moving in circular. It's a paracyclic reaction. So this pi bond is going down to create the new sigma bond. This one's going here to create, to move that double bond. And then this sigma bond is breaking to give us our next pi bond, okay? We have several types of these. They actually named reactions. So the Cope, oops, let's change the Cope rearrangement. And if you think about this one, there's no way to tell if this really occurs. But if we look at the Cope rearrangement, here, if we have a substituted species like this, right, it actually turns out that it's going to be driven in the forward reaction to give us this product, right? If we think about that, the reason that that's driven forward is that I have a more stable alkene now, right? So I go from a mono-substituted to a di-substituted alkene at the top. So that's why the Cope rearrangement works. Claisen rearrangement. And this one, we actually have oxygen in the species. With the Claisen rearrangement, okay, we have an oxygen in the ring. So we still have the double bond, right? So it's the base same structure, but now we have the double bond in there. Again, this is going to favor the forward sigmatropic rearrangement. If we look at our arrows, right, this is going to come down and make a bond here, there. I didn't do it up here, but it's the same thing, right? So then what results, right, is now we have a carbonyl, right? And that's going to be one of the driving forces, is to create that carbonyl over the ether, right? And so this is actually a pretty straightforward reaction. So in this case, we get 90% here, 10% favored there. Now, they aren't always shown like this, right? Usually what you'll see is an allylic group with a vanillic group, right? So then this will change up to give us that. One of the classics ones is on an aromatic. So if you take a phenol, right, and add an allylic group to that phenol, we can then heat this up, right, and that is going to give me carbonyl. And as we'll see in the next chapter, this does not stay that way very long, and that will tautomerize to give us back our aromatic, right? But what we've ended up doing is we've made a carbon, we've added a carbon to that aromatic group, right? So synthetic uses here is that carbocation addition. So you may want to remember this one for synthetic. All right, so most of what we're going to be dealing with in this chapter was the Diels-Alder. So let's do a couple more Diels-Alder reactions just to see, just to give you a little bit more practice. Okay, so give me the product of this one. And on both of these, give me the major product. If you want to pause right now, that'd be good. Yeah, and then we can go forward. I went a little longer on the last video than this one, so that's why this one's a little shorter. I probably should have stopped a little earlier. I think you ended up with the same amount of contact I would have covered. This is what my goal was for this week. Okay, so on the first one, right, when we look at this one, we have to remember that we're going to make one. We already have one 6-membered ring, so we're going to make one, right? And I'm going to put, let's color code this, right? So here is this triple bond, but it's a triple bond, so it's going to go to a double bond. And then because of the favoritism of endo based on the transition state, go look at the other video, right? We're going to get endo as our major product. On the other one, what we need to remember is our regioselectivity. So here on this other one, we're not looking for endo or exo, we're looking for regioselectivity. And what we need to think about is our partial positives and partial negatives. Okay, so we can draw resonance structures, and please take time to do that if you want to, or go back and look at the other video. Here's our partial positive. So that means when we bring these two together, what I want to do is rearrange this. All right. So I have my partial positive and my partial negative together. And that's from the resonance structures, which means that my major product is not going to be the 1,3, but will be the 1,4 product. Okay. So there'll be some practice problems up on this online, and please just take your time going through chapter 16. This is really the majority of what we needed to go through. When we get back next Tuesday after Labor Day, we'll start on aromatics. So if you want to read ahead, please do. But right now, I think with the last video and this video and not taking time for y'all to try this, this is sufficient. So